Hi, this is Shortly Physics, Session 2 for exam review. We're covering forces and Newton's second law today. Now, again, these are some of my old notes. I'm just going to annotate them as I go through. Just to introduce different forces, the first one we're looking at is friction. We're going to go through weight as opposed to gravitational force, Newton's gravitational law, spring force, centripetal force, normal force and apparent weight, and many examples. So I'll try to get through our main examples that cover the main concepts. So our first force I want to cover here is friction. A little bit of emphasis on normal force, and I'll come back to that later. So when looking at an object going across a surface, if it's pushed with a force, F, it's going to experience friction between those two surfaces. Now this friction is not air resistance or drag. This would be the rubbing force between the two solid surfaces. Now friction and normal force are really the same force. They're the contact force between the object and the surface. The normal force being the perpendicular component and the frictional force being the parallel component. And it always resists the force of the push. There are two kinds of force. We have static friction and kinetic friction. Static friction is also involved with rolling friction. If a car is rolling its wheels along the ground and those wheels are not sliding, then it is a static friction still. When you start hearing that squealing of the tires, then it gets to the kinetic friction. So here are a few standard scenarios. You've got a object being pushed across the horizontal ground. It could also be an incline. We're going to look at an incline later on in the example. You might also have an object pushed against a vertical wall. So if there's a force pushing in, then there's a normal force pushing out. That normal force is always perpendicular to the surface, and the friction would be parallel to the surface. So in both these cases, you see friction parallel to the surface, there and there. The normal force is perpendicular. Now, if you push an object against the wall, it's the friction pushing up. It keeps the object from falling or sliding down. If it's an object on the ground, it's the normal force that supports the block, but it's the friction that pushes up, supporting the block. It's the friction, again, trying to oppose that motion. On the vertical wall, it's the friction's opposing the downward motion. On the horizontal surface, it's the friction that's opposing the sliding motion. Now, friction is proportional to mu, which is the coefficient of friction that describes the magnitude of grip. You can think of it like that. How well do these surfaces that are in contact grip to each other? And you can think of that like at the subatomic level. Excuse me, the atomic level of the surfaces. The atoms are interacting. They're either pushing perpendicularly for the normal force or parallel for that friction, and sometimes it's mainly a combination of both. They grip at that atomic level, not subatomic level. So when an object slides over another object, the amount of grip, that friction, would be the mu kinetic coefficient of kinetic friction times the normal force. Now oftentimes the normal force is equal to the weight pulling it down. However, be careful if there is a force pushing downward or a component that has a downward component, up or down, then that normal force would not be equal to the weight. So just don't get tricked by that. If you're dealing with an object that is at rest with a pushing force, trying to push it, but there's enough friction to hold it, to keep it from moving, then you've got static friction. And static friction is less than or equal to mu static times normal force. Now this is the general case for static and kinetic friction. Notice I don't have it labeled as a K or an S. So if we did plot a pushing force, let's say for this block, if this F is the pushing force, then as we push with more and more force, what will happen to the amount of friction on this axis? So the greater and greater the push, the more static friction there will be until it reaches this maximum where mu s times normal force is equal to that pushing force. At that point, it's going to break down, of essence. That static friction is going to release, What's happening there at the atomic level is those atoms are being pulled so much that they just start to slip. Okay, so there's a greater and greater and greater pull until it just starts to slip. At that moment, kinetic friction takes hold, and it is less than that maximum static friction. So immediately, the frictional force will bump down, and so there we go. It'll bump down and then remain at a constant kinetic friction level. That happens when you're cutting a bagel. You're cutting the bagel mistakenly with your hand underneath the bagel. So as you cut down, the knife sometimes gets stuck with that static friction. So what do? You push and you push and push, and then slip, and you go to the hospital, the emergency room, because that frictional force that you're experiencing is finally overcome, and you only have this lesser amount of kinetic friction, and that's not enough to keep that knife from slipping very quickly. Moving on to weight. Gravitational force equals mass times the gravitational field, also called the acceleration due to gravity. This is very similar if you've taken AP Physics 2, or if you might recall, electric field is very similar in that form. Here, gravitational force over here, and then we have the electric force over here on the right, and they're equivalent to the property of matter, whether it's a charge or the mass. Here's the property, mass over here and charge over here, times the electric field for this case. So that means this little g is the gravitational field, mainly at the surface of the planet. That's generally where we use little g. So g is the acceleration due to gravity, but it's also the gravitational field strength at the surface of the planet. On Earth, it's 9.8 meters per second squared. That's always a good one to memorize. Now, gravitational force, this is more general for all cases. You can find the gravitational force at the surface of the planet if r is the radius of the planet and m is the mass of the planet. You'll notice in this form, though, this is also gravity, just like the weight equation. So if weight is mg, then gravity is also mg, where the m2 over here might be the m up in weight, and the gm1 over r squared would be the gravitational field strength. Now g is a constant. You can always look that up on the equation sheet and table information that the College Board will give you. So it's 6.67 times 10 to the negative 11. This does indicate that gravity is a weak force and requires two large masses, or at least one large mass, to make it a significant gravitational force between the two. So this Fg is the force of gravity between two masses a distance r away. So here's mass 1, mass 2, and the distance r. Now it's important to note that the r is measured from the centers of mass of the two masses. So therefore, if you're standing on the planet, the center of mass is here, and here's the object on the planet. You would measure the r between the center of mass of the Earth and the center of mass of the object. Generally, that's the radius of the planet. That's where we live. Moving on to spring forces. Hooke's law. F equals negative kx. So the negative indicates that this is a restoring force. It is a conservative force. When we get to a discussion on energy and work, there are conservative and non-conservative forces. So gravity is a negative force. You should technically put a negative out here if you put this in the put this gravity equation in a force form. So this is a force vector of gravitational force. There would be a negative out front to indicate a negative direction going in towards the radius. Down here at the spring, this negative indicates it is a negative force also. So if there's a positive displacement and with a negative in front, the force will be in the negative direction, or the opposite direction of the displacement. So if you stretch the spring downward by the weight on the end, then the restoring force of the spring is upward. That's what that negative intones. Now we get to the K, the spring constant. Each spring has a different spring constant. The loose springs have a low spring constant measured in newtons per meter, and the tight springs have a high spring constant. So if you think like 10 newtons per meter, versus 20 newtons per meter. The higher spring constant, 20 newtons per meter, would pull with a greater force if you stretch it out 1 meter. Generally, springs aren't that long, so generally you're looking at 20 newtons per meter would be about 5 newtons for stretching it 25 centimeters, or 1/4 of a meter. In a force diagram, if you've got a mass hanging on the end of a spring, then the weight pulls down and the spring force pulls up. And it's easy to measure the spring constant that way. If you ever need to come up with a laboratory procedure for measuring spring constant, simply hang several different masses on a spring, kx going up minus the mg, the weight going down, equals 0 acceleration. If you hang it so that it's not bobbing up and down, if it's at rest, the acceleration of the spring is 0. That means kx equals mg, and you can calculate the k value that way. A better procedural way to do this would be to measure several different masses and plot them on like a force of the spring versus displacement graph. And if you plot force of spring on the y-axis and displacement on the x-axis, then the slope of that line will determine the spring constant. That's a better procedural way to come up with an accurate spring constant. Moving on to centripetal force. Anytime there's a spin, circular motion, think of centripetal force. You could be on some seemingly unrelated note, question on the AP test, and if it mentions circular motion, please put this in the back of your mind. And you solve these any other way, just like any other Newton's second law application. You start with sum of the forces, set them equal to ma, but instead of an acceleration that speeds objects up or slows them down, this is going to be acceleration that changes direction. So the only thing you do differently is you figure out the force, the direction of a force where there would be a centripetal force. In this case, we have a mass that is moving with a circular motion on the end of a string, and there's a tension pulling towards the center. We're going to identify that direction as the direction of the centripetal force. So I'm going to use that in this case. Here we go. Tension would be the sum of the forces in that direction. M would be the mass on the end of the string. And then finally, the acceleration, we're going to substitute v squared over r. And that's how you solve for that scenario. If it's a car going around a turn, there's a tangential velocity of the turn, a radius of the turn, and friction pulls them towards the center. So we're going to make that our direction for Newton's second law. Friction equals the mass of the vehicle times v squared over r. Or let's say it's a satellite going around the Earth. Here's the Earth, here's the satellite. Earth is mass 1, the satellite is mass 2. Gravity is the distance between them, and r is that orbital distance. So Fg is the force, the net force. M2 is the satellite that's spinning around in the circle, and acceleration would be centripetal acceleration, v squared of r. Plugging in Fg equals gm1 m2 of r squared. Of course, we'd substitute in the mass of the Earth. M2, notice M2 would cancel out on both sides, leaving us with a v squared over r on this side, and one of those r's would cancel. R, multiply r on this side, and multiply r on this side. You end up with a simpler expression. All right, so that kind of goes quickly through several common centripetal force scenarios. Moving down to normal force and apparent weight. All right, apparent weight is normal force. You apparently weigh a certain amount, like let's say you're just standing on the floor or sitting on your chair, watching this video. Then the weight that you feel against your tush is the normal force pushing up. Now, what if you were sitting on a chair in an elevator and it began to move downward? In an initial period of acceleration downward, you feel a little more lightweight. So in that case, the upward force from the floor is not as great as the weight pulling down. So the normal force is less than your weight. You'd apparently feel lighter. Or if that elevator started moving upward, you'd feel heavier for a moment as it accelerates. So in these cases, if there's like the room that you're in is moving, then you've got an apparent weight scenario. And basically, if a question ever asks for what is your apparent weight, just consider what is the normal force. So you'd set this up. Here you are as the object. The normal force from the floor of the elevator is pushing up. There's a normal force. And your weight is pulling down. Now, if the elevator is accelerating upward, you might draw this normal force greater than the weight. Or if it's accelerating downward, you may draw the normal force less than the weight. What's not changing is your actual weight. You won't be attracted toward the earth any more or less, whether you're moving up or down in the elevator, but the elevator is supporting you more or less in those two kind of scenarios. So if the elevator has zero acceleration, then your normal force will equal your weight. If the elevator's normal force is greater, so if it's accelerating you upward, in this case, the acceleration is 2 meters per second squared up, then the normal force minus the weight is equal to m times 2. And in this case, instead of weighing just as a 50 kilogram person, instead of weighing just 500 newtons, your acceleration over here would be, times the mass, would be 100. So when we add 500 right here to 100 on this side, you'd apparently feel like you're 600 newtons instead of 500 newtons. Or if you're accelerating downward, again, set up the same way. Normal force minus weight equals mass times -2. In this case, we'd end up subtracting 100 newtons from our weight. So we don't feel like we're weighing 400 newtons. Okay, some other cases. What if you're at the bottom of a hill? Centripetal acceleration is always toward the center of the turn. So I'm going to make that positive. Normal force minus the weight of the moving vehicle equals, but in this case, the acceleration isn't like 2 or -2. It's v squared divided by r. So we're going to put the positive normal force in the direction of the centripetal force toward the center of the turn. So that equaled mv squared of r. And we'd be able to solve for, depending on the velocity, be able to solve for the apparent weight, how heavy you feel. So when you're at the bottom of a roller coaster hill, you always feel like you're pressed into your seat, you're heavier. Or at the top of a hill, you feel lightweight. Sometimes you get that kind of like an air time, you get that lightweight feeling. So at the top of the hill, downward would be the direction of the positive centripetal force. So I might use mg minus Fn equals mv squared of r to solve for that one. And that will give you the proper direction. All right, and that comes to the end of our forces showcase. So I'm going to move on to solving some scenarios. Here's the one I was just talking about. Whenever we approach these, we're going to draw a force diagram. We're going to resolve the components. Actually, before you do that, you might consider a frame of reference that is most appropriate. Whatever the direction of acceleration of your object is, make that in the direction of your x or your y axis. So if there's a slope, you're going to kind of look at it like this. All right, make this your x, make this your y. If we're talking about an object like here, like the bottom of a hill, and solving for apparent weight, I'm probably going to make up in the y direction my positive. Okay, so that's the direction of the acceleration. All right, so force diagram, it's your first step. Consider your frame of reference, give your best reference frame. Then draw a new diagram with the any angled forces resolved. So break up those forces into components. Then we're going to apply Newton's second law in the x and the y direction. That gives us two equations of motion, or two equations for solving a system of equations. Then we're going to solve for the unknown or unknowns. Okay, so the first thing I'm going to do in this situation, at the bottom of a hill, we're going to draw a force diagram. There it is. Up is the direction of the centripetal force. So also writing out your givens is very helpful, so you don't have to go looking back into the question over and over again. So draw the force diagram. My frame of reference is good, so I'm going to leave it like that. There's no angled forces, so I considered that. So I'm on to applying Newton's second law. F equals ma, sum of the forces. So I got sum of the force is the normal force minus the mg weight equals mv squared of r. I'm going to plug in my knowns now, see how this That's how easy it is. The M plugs in. The G is 9.8 or 10, so make sure you just show that in your work, whichever value you're using. The velocity over here is 20. The radius of the turn is 100, and we solved to get 700 newtons instead of 500 newtons, so you'd feel heavier in that case. If the car is at the top of a hill, you feel a little lighter in weight. So there's two ways to look at this. You can either keep up as positive, but then acceleration would be in the negative direction down. I like solving this the other way. I'd probably put, if I did this again, I'd do mg minus fn equals m positive v squared over r. You'd get the same result in the end. Okay, but in this case, work through that similar kind of math, you'd get 200 newtons less in weight on that same 100 meter radius turn. All right, moving on, getting a little friction in here. Friction on a horizontal. We've got normal force up, some kind of pulling force, friction pulling back, and weight. So we're going to solve for the force so that the box's acceleration is 0 and if its acceleration is 5 meters per second. So those two cases. So here we have in the x direction, the force pulling the box minus the friction equals mass times 0. Now at this point we'd substitute force of friction equals mu times normal force, and therefore the pulling force friction equals mu times normal force 0.2 times 200 for the given values. 20 kilograms is the, oh, where did I get that from? The y direction. So if you're ever unsure, what should I plug in for normal force? Let's check out the y direction. Don't be too quick about this. Some slightly more complicated scenarios may have like a force pushing down or up, maybe with a component. So you wouldn't want to accidentally forget that in your normal force. So it is good to consider the y direction. Here I have normal force up minus the weight down, and the weight is 20 kilograms times 9.8 or times 10. So normal force minus 200 is 200 newtons. And that's what we plug in down here, times the normal force gives us 40 newtons of friction. Well, what if the acceleration is 5 meters per second now? We'd still have the pulling force friction minus mu times normal force, which is still, the normal force is still 200 newtons. But in this case, we'll have the mass times 5 meters per second squared of acceleration. So if this is the case, then we're going to have a force of 140 newtons. You calculate all that out. Okay, moving to a friction scenario, but with an angled force. This is where I was saying you got to be kind of careful. Careful with that y direction. I do recommend starting with the y direction. If you do notice, if you have a friction scenario, this might be a sled being pulled along the ground with some kind of angled pulling force. But we're going to start with that y direction just so I don't accidentally flub up the normal force calculation. So what is the pulling force if the acceleration is 0? What do you mean it's pulling with 0 acceleration? Well, just remember you could be pulling at a constant speed and the acceleration would be 0. So I'm going to draw a force diagram. Then I'm going to resolve the forces into their components so that pulling force turns into an F sine 30 and for the y direction and F cosine 30 for the x direction. For that y direction, we've got a normal force up plus F sine 30 minus mg down. So that's what the y direction equation is going to look like. F sine 30 plus normal force minus the weight equals 0. Simplify that as much as we can, and we end up with two unknowns, the unknown pulling force F and the unknown normal force. The weight gets pulled over to the y to the other side. The m times 0 is 0. My brain was going, there should be a 0 on the other side. No, we're going to pull the weight over. So the F sine 30 plus the normal force is equal to the weight down. So when we simplify as much as possible, we end up with just a F sine 30 times plus normal force equals 200. So we actually have to stop right there. These numbers down below aren't coming into play yet. So what we don't know is the normal force. We're looking for F. So then we go to the, when you get stuck, don't stop, go to the X direction now. In the X direction, there's F cosine 30 to the right, and this is friction to the left. Now it does specify that the acceleration is 0. So therefore, F cosine 30 to the right minus the friction to the left equals mass times 0, and F cosine 30 is equal to 0.2 times normal force. And from that X direction, I'm getting another relationship between normal force and the pulling force. So now I have a system of equations, two equations. Here's one, and here's the other over here. Two equations with two unknowns. I solved this one for normal force. I'm going to plug it in right over here. So you get F sine 30 plus F cos 30 over 0.2 equals 200. And we do some magic algebra to get a pulling force of 41.4 newtons. Okay, so there's one situation scenario pulling horizontally, and now we get to our final scenario, friction on an incline. Here we're looking for the acceleration of a block down the incline. There's no pulling force up. So as it accelerates down the incline with some kinetic friction, that kinetic friction is going to work at an angle. The normal force is always acting from the surface up, and the weight always pulls from the center of mass down. So in this scenario, the acceleration is down the slope. So notice what I do here. I'm going to transform this into a new force diagram with my new perspective. I want the acceleration to be in the X direction. That means the normal force is going to be in the Y. And if you track this Y direction down, the weight from this new perspective is pulling out here at an angle. So before I move on, I'm going to interpret that angled force into its two components, Y and the X component. In this case, don't move it too quickly. The horizontal component in this perspective is the sine piece, because my angle is measured from the vertical, the 30 degrees. So the downward component of that weight force, the downward meaning that the component into the surface, perpendicular to the surface, is mg cos 30. It's adjacent to the 30-degree angle. That leaves the opposite side. This component down here is the component that's parallel to the surface, the mg sine 30. Now, take a moment back, step back, just to remind you about this angle here. You see that the theta is 30 degrees, and that's measured up from the horizontal to a direction parallel. Now, if I start with a surface that's horizontal, the normal force is straight up and the surface is parallel. If I angle that surface by 30 degrees, look what happens to this vertical component. So I angle the horizontal surface up 30 degrees. The vertical component is angled 30 degrees from the vertical reference. Okay, so likewise, the weight that was in the vertical reference is going to be moved an angle theta from the vertical reference. So if the angle from the horizontal reference describes the slope going up, that's going to be the same angle measurement from the vertical reference. All right, so that gives us our cosine 30 downward and our sine 30 to the left. We've got friction going up the slope. In my new perspective, that's directly to the right, and normal force is perpendicular to that slope. So I start with the X direction over here, and then I'm going to go to the Y direction. That gives us a system of equations. So in the X direction, just using this force diagram over here now, I've got mg sine 30 to the left minus the friction to the right equals ma, and we're going to be looking for the acceleration rate, so we're going to leave a there. It's not 0 in this case. And we get stuck right there. When you get stuck, don't stop. Let's move over to the Y direction over here. The Y direction has normal force up minus mg cos 30 down, so normal force minus mg cos 30. And this object is not accelerating up out of the surface or down into the surface, so the vertical, the A direction acceleration is 0. So when we when we solve for normal force, that's equal to mg cos 30. We're going to plug that in right over here. mg cos 30, our m's end up canceling, ma, mg cos 30, mg sine 30. The m's cancel, and we get a g sine 30 minus mu k cosine 30. Mu k is given in this problem. So plugging in all those known numbers, there's g sine 30 minus mu g cosine 30, and we get an acceleration value. So there are many different scenarios that may come about from friction and slopes, but this is the main few. And thanks for watching.